Hey, welcome everybody into the NGK Tech Garage. Sorry that we're starting a little bit late today. Had a little bit of network technical difficulties. I'm having to monitor comments via the phone today. We're having a little bit of firewall issues or something going on, but it's not going to affect the video today. So if you see me constantly looking down, looking at this, I'm just checking to see if you guys have questions or something like that. So today we are working on a 2005 Chevy Express van. This is a 1500 two-wheel drive with the 4.3 liter V6 in there. And as many of you guys have probably run into before, it's got the false activation of ABS or ABS activation on dry pavement, coming up to a stop sign, low speed type of thing. Kind of a common issue on these 2000s eras Chevy and GM vehicles, especially the truck bodies. So there's a couple different ways that we can tackle this problem, a couple different tools that we can use. We have out the scan tool today, multimeter that is stuck to the table, and the lab scope is also out. And then over here is a test fixture that actually our engineering department uses in order to test out sensors. So we're going to play around with that a little bit today, do a little bit of experimenting, and then we will diagnose this problem on this vehicle. So, all right, chat is very busy. It's good to see you guys. That is awesome. And yeah, like I said, I'm not able to monitor chat via the laptop today, unfortunately. So I will be watching on here. So let's get right into this. First problem is that this thing doesn't have an ABS light on. Now it's pretty common for these failures to run into this problem without setting a code. So let's just go ahead and grab our codes real quick and see what we've got. So I've already built the vehicle. We're working on a GM Express Savannah, whatever, 4x2, no fault codes detected, which is exactly what I expected to see. But the complaint again is that this thing rolling up to a stop sign, that ABS is engaging on completely dry pavement. Now, it snowed out here yesterday, so we don't have any dry pavement, but I was able to capture some data beforehand to share with you guys. So let's go ahead and grab that now, and I'll show you guys what I've captured on here. So all I've done is I've graphed the wheel speeds while taking this thing for a drive. While somebody else was driving, I was monitoring the scan tool, of course. So we'll just go ahead, open these into graphs. And we'll zoom out a little bit on all of these. And again, this is a two-wheel drive vehicle, so we're using a 3-sensor ABS system. Left front and right front both have a wheel speed sensor, and then there's one for the rear. And for those of you who have good eyes, you can probably already see that there's an issue, but let's back this up a little bit. You can see here we're increasing in speed and then decreasing in speed, and everything looks pretty happy, except we have some discrepancies in our frames here. So if we start scrolling ahead on here, we'll get an even spot. And you can see that our left front speed sensor and our right front speed sensor are reading different. Now, for whatever reason, the scan tool doesn't interpret 0 miles per hour on these sensors. For whatever reason, when it's reading 0 miles per hour or less than 3.11 miles per hour, it just reads 3.11. So you can see we're flatlined here because our sensor isn't responding. And there we start getting some response. And after we're over a certain mile per hour, we actually start to see the sensors lining up properly. Let's back this up a little bit so I can grab you guys a spot here to show that it's actually accurate. So we're all reading 11.81 at this point right here, right? So we start to come up to a stop sign, we're slowing down, we're coasting, and right about here is where our issue happens. So we're scaling down, right? We're slowing down 8 miles an hour, down to 6 miles an hour, and then we drop out. So you can see a really sharp drop off there, right? If we zoom in, and we zoom in this one, you can see this one kind of has a staggered drop down where this one has a pretty sharp drop down. Our sensor at that point is dropped out. We no longer have enough signal coming out of that sensor to trigger the computer to monitor or show that wheel speed. So at this point, the vehicle thinks, or the ABS module thinks, that we're coming up to the stop sign and the right front has locked up for whatever reason. So it engages the ABS brakes, right? We don't want the wheel to lock up. We don't want it to flatline if our other speed sensors are telling us that the vehicle's still moving. So our right front is locked up, we engage the ABS brakes, and now we have that false activation is what I like to refer to it as. But because we're at such a low speed like this, we're actually not going to set a code because it's just, the computer just thinks that that wheel has locked up upon stopping. So we don't have any codes, but we have an obvious issue here with the right front wheel speed. Eric's got a good question at why they start out at 3.11 miles per hour. My guess is because it's got something to do with the threshold at what the voltage level is required for the ABS module to start picking it up. There's going to be a certain output voltage that sensor is going to create, and actually there is a sensor sitting in this test fixture right here that would go on this vehicle. But there's going to be a certain voltage level that has to be output in order to cross a threshold that the ABS module is looking for. The ABS module is looking for whatever voltage it might be, then it starts to pick that up, and then it starts to look at that signal. So we have a sensor on the right front that's dropping out, and our left front looks good, right? So if you go into service information, it's always a good idea to first of all check what type of sensor that you have. Now this is a 2-wire sensor on here. If we look at a wiring diagram, we'll find that this is just a variable inductance style sensor. So if we just grab an OE diagram for ABS, and we'll grab our front sensors. Like most, no, not like most, but in the Chevys and GMs in this era, they're a 2-wire sensor that is fed low reference. So there's basically a ground here that's slightly off of ground, and then a signal wire. So as this trigger wheel here, right here, which is actually internal of our wheel bearing, as that spins around, we interrupt a magnetic field within this sensor right here, and we create a voltage level, okay? The faster we spin the wheel, the faster we spin that trigger wheel, the more voltage that we're going to create. Okay, that's the way a variable inductance sensor works. So we don't have to feed it power, we have to feed it ground, and we have to monitor the signal. So if you were to follow service info and that kind of thing, chances are you'll probably be doing an ohm test first. That's what a lot of people will do on a sensor. So let's just go wheel speed. Oh, let's grab a C0050 because chances are this is one of the front wheels. There we go. So a C0050 code would be a right, that's right rear and left rear. We don't want rear, we want front. So it's not a 0050, it must be a something else. Maybe a 245. Yeah, it's for the rear also. Well, we don't have any codes. I was just trying to grab you guys a spec of the resistance on here. But that's all right. Let's see if we can find anything in here. Wheel speed sensor replacement, 2-wheel drive. Let's see if there's anything in here. Nothing in there. Diagrams, components. So there's no spec post on here. So now you don't have a spec to go off of. If you want to do a resistance test first, let's do some comparative testing, right? I mean, that's kind of a good way to verify. We know our left front's working properly, but our right front is causing us issues according to our scan tool, and we're getting this ABS activation at low speed. So you can use a meter for this. You can use, whatever you want, but a meter is going to be the quickest, easiest thing to grab. If you have your scope out already, you can put it in the ohm meter mode, but that's up to you. So we have our left front. We have our, we have our left front already hooked up right here. I ran some wires over here, and our right front here. So let's start by checking out our known good. So let's plug it in. And we're at 3 million ohms of resistance, but that's without the sensor unplugged. So I'm going to go over and unplug the sensor because we want to isolate the sensor from the system whenever we're doing our ohm testing. So I have the sensor, and there we get the dinging of the chime because the key is on and we just unplugged our wheel speed sensor. And of course we're going to read open because apparently my piercing probes have fallen out. There we go. And that's roughly what I would expect to see. We're coming in at about 991 ohms, so just under 1,000 ohms. And that's pretty common spec for wheel bearings. You want to be around that 1,000 ohm mark. So let's go ahead and grab the left front speed sensor now, right front, and take a look at what that reads. Oh, now the thing's really mad. All right. So all I've done is disconnect the harness behind the wheel here, and we're just going to do an ohm check on this one. And my gut says that this is going to probably be okay because our sensor is reading properly all the time, except for that really, really low speed. So we go ahead, get hooked up, and now we're just reading the value across the sensor, and we're at 1,030 ohms, 1.03 K, 1,030 ohms. So we're right there for both sensors. Both sensors are reading roughly the same ohm reading, okay? It's not high or open. If we saw 500,000 ohms or 1,000,000 ohms, it would most likely be an open circuit. If we saw really low, it'd be a shorted sensor that's not able to read properly. So we kind of figured we didn't have an open sensor, right? Otherwise, we wouldn't be picking up a speed at higher speeds. So we knew that we didn't have open, but it's possible that sensor could have been partially shorted, right? It's possible to have a sensor partially shorted where, let's say our ohm reading on there was only 500 or 200 or 100 ohms. It's possible that that sensor could still create voltage when the tone ring there is being spun around, but it might not be able to create enough. When our resistance goes down, our magnetic field has shrunk, and it's not as, let's call it, as sensitive to the vehicle. So by changing our resistance value of our sensor, it could change the overall output. So when we're looking at a two-wire, yeah, the whiteboard, I get to draw a little bit here. We'll see how I do. When we're looking at a two-wire sensor, like this variable reluctance style sensor, we're basically looking at one long piece of wire. So we have our, let's call it our one wire coming in, and then that wire's taken and wrapped around a bobbin inside of there, and then that wire leaves, so we'll call this down here ground, and we'll say this is the signal that's being monitored by the PCM. It could be flip-flopped. It doesn't really matter at this point. All we're doing right now is we're measuring resistance between this point and roughly somewhere in there, okay? We've taken this out of the circuit. Now we're measuring resistance across this long piece of wire that's wrapped around a whole bunch of times. So it's supposed to be within a certain resistance spec. And I'm going to call it 1,000 ohms or so on these vehicles. But if we were to short this sensor out, we would be taking our long piece of wire and we'd be finding a shorter path, a path of least resistance, right? So what we could have is these wires inside aren't supposed to be touching. They're coated with an enamel coating so that they're not touching. But if those wires start to make contact with each other, now our really long piece of wire could be shorting out between here maybe, or maybe between here, whatever it might be, but we've taken this long piece of wire and we've shortened it down, all right? We still have some resistance there because we're still going through a relatively long piece of wire, but it's now shorter to the point where our overall resistance now, let's say it were 500 ohms, okay? So at 500 ohms instead of 1,000, now our output voltage out of that sensor is going to be less. So we've shorted a sensor. We haven't completely shorted it to where we've connected basically these points. So now we have like 0.1 ohm of resistance in there. We haven't completely shorted it, but we've reduced its efficiency. We've reduced its sensitivity to the point of it's not able to put out an accurate signal. It's not as strong of a sensor, okay? But that's not what's going on here, right? Our ohm reading is 1,000, call it 1,000 ohms on both sides. So we don't have a sensor issue per se. Now it's possible when heat cycled that this thing could change its ohm value, right? If we get this thing really hot, get the brakes really hot, the sensor heats up, maybe the resistance value goes up or down or something changes with it. But let's check to see if we actually have a issue right now in the shop with this thing. This thing's been sitting in here overnight, so it wasn't going to be dripping snow on me. But let's plug these guys in, get the scan tool up on live data, and let's take a look and see what we actually have for wheel speed in real time. All right, so both sensors are plugged back in. Let's exit out of here. Let's go back to our vehicle. Let's go into live data. And we'll grab our wheel speed. All right, so again, we're reading at 3.1. And we'll start spinning the right front. And now, unfortunately, being a two-wheel drive vehicle, spinning this thing by hand, it's hard to get a consistent speed with it. But let's see if I can do that same thing on the left front and see if we get any response out of it. So roughly the same speed, and I'm getting a signal. All right, so I've spun them both at, well, it's not a super accurate, but I spun them both at roughly the same speed, and I get nothing out of this sensor. But if I can get this one going fast enough, there you can see we get a response out of it. But then it drops off, right? So those really, really sharp edges there, we're missing that at a really, really low voltage level output. So let's do a little bit more comparative testing. Let's grab the multimeter. Whoops. And we're going to unplug the sensor right now. And I'm going to do a, actually, you know what, better yet, let's pierce the harness. So I'm going to pierce the sensor harness on here, the sensor side. I'm going to pierce this so that way we can leave this thing plugged in, monitor on the scan tool, monitor on the scope, and monitor on the meter. And let's see what it looks like on a little bit of everything. Now I believe that this is all original on this side. I don't think any of this has ever been changed out. So pierce that one. And if you don't end up replacing the sensor or the harness on here, make sure you seal this back up, okay? You don't want to leave those piercing holes open because you will end up with an issue in the long run, right? You'll have corrosion entering in there and you'll have a bad spot in the harness, okay? So let's take, and we got to go on volts AC because we're creating AC voltage when we're using a two-wire sensor. We're creating AC voltage. And let's see if you guys can see this. If we switch over to the other camera, they might be able to see as I spin this around. Trying not to get my wires tangled. Maybe. Want to flip over to the other one? We'll see. There we go. So even at a very, very low speed, all right, we're still creating some AC voltage, but it's not enough to trigger the scan tool. Can we bring up the scan tool in the corner as well? There we go. So spinning the wheel, creating AC voltage, but it's not enough to get the the ABS module to trigger it. Let's jump over to the other side now. And I got to plug that one back in. All right. Oh, sensor is plugged in. So we'll see here if you guys can maybe see that as I spin the other wheel. Maybe. You want to flip over to the other camera? Maybe they'll be able to see it then. Nope. All right. We'll see if that stays there while I spin this wheel. And I'm spinning it at roughly the same amount of speed, but you can see we're getting a reading that's higher, right? Our voltage level is higher, and our scanner picked up, our ABS module picked up the signal input, okay? So we have different voltage level outputs from our sensors right now. So let's actually compare in real time on the scope what it is that we're reading. So we'll hook into each side with two separate channels on the lab scope, and we'll do a little bit of comparative testing that way. Then maybe we can see the actual voltage value that's required to get this thing to engage and actually record some wheel speed on the scanner. All right, so we'll open up the scope, switch our channels over to AC, throw on our voltage scale a little bit higher there, and we'll grab kind of a wide shot here. We'll grab 20 seconds per division. Actually, we'll grab 10 seconds per division, and then we'll zoom in afterwards. So start by turning this wheel. All right, and now I'll go over to the other side. And can you bring up the scan tool on the screen as well? So that one didn't trigger the scan tool at all, or the wheel speed at all. Now I go over to this side, spin it at roughly the same speed. And we should have triggered on the tool as well as seen this. Okay. So if I stop this here, go ahead and zoom in on this, and our peak voltage here, we'll call it 200 millivolts. And our peak voltage here, we'll call it 350 millivolts or so. So we have two different amplitude levels, right? Our signals are at different levels, okay? So we kind of already figured that because our sensor's not able to create enough voltage on our scanner, our sensor's not able to create enough voltage coming out of the sensor, our ABS module can't pick it up. We're running into issues that way. But what's going to cause that problem? Why are amplitude levels different if our resistance is the same? Both sensors are coming in at the same resistance, but their voltage levels are different. And also, did you notice that with this guy, we didn't read the exact same voltage level that we read on the scope, right? Just remember, when you're using a meter, the voltage output that you see on the meter is usually going to be less than the peak voltage that you see on the lab scope, okay? Because of the refresh rate. So this thing's reading a handful of times per second, where currently per second we're reading significantly more, about 4 million samples. So our sample rates are a lot different tool to tool. So just keep that in mind, that your voltage level will most likely be a lower output level with a meter than with a lab scope. All right, so we know now that we have something that's causing our sensor not to create as much voltage. But the resistance on both sensors is, for all intents and purposes, exactly the same. We'll call it 1,000 ohms on both sensors. Let me just make sure that we're not... God, you guys are talkative today. Yeah, so you guys already have a good idea. All right. So again, our voltage level is different. So what is causing that difference? Well, when we get the sensor creating its voltage and we start to interrupt that magnetic field with our tone wheel as we spin this guy around, The faster we spin this, the more voltage we create, right? As I spun the wheel faster on the scope, you can see that we've created more voltage on here, right? As we rolled this thing faster, I was able to create more voltage. So at some point here, we crossed a threshold to tell the ABS module that the wheel is spinning and we should start recording that data on our scan tool, right? So we're peaked at about 200 millivolts here, and I didn't get the scan tool to react at all. Here, we're peaked, Here we're peaked at, what is that, 300 and whatever millivolts, and we got the scan tool to react. So that's that voltage that it requires to react. But what's going to change our voltage level? That's not resistance, and it's not speed. So we're at a very low speed, and the biggest problem with these is the air gap. All right, so when you install the sensor, it reads a certain distance from this ring right here, okay? So if we actually take a close-up look at this guy right here, you can see this isn't the exact tone ring that's inside of the bearing. This is one that we just had sitting here, but this is the sensor that belongs in this vehicle. And you can see we're a very, very, very close gap between there, and if we measure with a feeler gauge right now, I'm at about 20,000th of a gap, okay? So if I take and we'll throw this thing on the lab scope, and we'll try to get some voltage levels readings out of this thing. All right, plug it in. So if I turn this on, and we'll start off going pretty slow. That's about as slow as I can get it to consistently spin around. We come back over here. So even at this speed already, we're already creating a pretty high voltage level, right? I mean, we're peaking here at, what is that, maybe 3, let's call it about 3 volts, right? Roughly 3 volts here. And so this would probably be enough to trigger on the vehicle to tell the vehicle that it is, in fact, creating a wheel speed. And actually, if that's plugged in, I bet we can tell the module that this side is spinning, just to do some testing. It's a little bit of experimenting. Oh, I must have a bad connection somewhere. All right, we'll mess with that in a little bit. So at this voltage right now, we are reading that, whatever, 3 volts roughly. But what we have happen with these sensors is we're not changing the speed at all, right? The vehicle's rolling down the road at whatever speed it's rolling at. You're not changing the speed in which this ring right here spins. We're not going to affect that at all. What we're actually seeing happen is we're seeing rust space this sensor away. So I'm going to take our air gap and I'm going to begin to increase it. Wait for the scope to refresh on the next screen. And I'm just spinning this thing a little bit. And you can see, now if I bring it back close, just by varying our air gap, just a tiny amount, thousandths of an inch, we are changing our signal's amplitude. But what hasn't changed is the overall frequency. So if we stop this here, the reason why our sensor is responding accurately once we've activated it, once the scan tool picks it up, is we haven't changed our frequency at all. So as long as we don't move our speed, we're at 30, let's call it 39 milliseconds peak to peak. If we scroll back here a little bit, we'll go to where the signal was a little bit larger, but still the same speed. We should see the same spacing in between. Roughly that 38, if I can get on the peak, roughly 38 milliseconds. So we've changed the air gap on that sensor. So between the sensor and the wheel, we've changed the air gap. but we haven't affected the speed at all. And that's why this sensor, even though it's not able to cross that voltage threshold at that very low RPM, the sensor is still perfectly accurate once we get up to speed with this thing, because once the ABS module crosses that trigger point, that voltage level, that whatever it is, 1 volt, half a volt, whatever it might be for that particular model, once we've crossed that threshold of voltage, we're really going to be looking at frequency at that point. So we change our frequency level when we change the speed of the wheels. So if I take and bring this guy back to real time, and now what I'm going to do is I'm going to leave our air gap the same, so everything there looks the same, but I'm going to increase the RPM on the wheel. So that's roughly double the speed or so. And you can see, obviously, we're moving the wheel a lot faster, so we're creating more voltage. But not only has the output voltage or amplitude changed, we have now also changed our frequency. So if we zoom in here, grab our cursors again. So we were at, what, 38 roughly before? Now we're at 6.8. So once we've crossed our threshold, once we've crossed that, whatever it is, 100 millivolts, 500 millivolts, whatever it is, once we've crossed that, we're now really going to kind of rely on frequency to actually determine our wheel speed. So our ABS module is really looking for two things. One, a certain input voltage, and then we're looking at frequency. We're going to monitor the frequency, and we're going to change our wheel speed accordingly. So once our sensor here, once our wheel is spun fast enough, our sensor creates enough voltage, we overcome that threshold. That's why we're able to get an accurate reading out of this thing once it is up to speed. All right, so I'm going to unplug that again, and I'm going to run some probes into here, and we'll just take this one step further, and we'll use the tester to run our actual wheel speed on here. So let's grab these leads, plug these in, and we'll see what we're reading currently. Of course, everything's tangled up. That'd be just the way it goes. All right. So we're not reading anything on the scan tool right now for some reason. Maybe because we've flagged a code, or because we unplugged our harness here. Hey, there we go. Okay. So we're reading 14 miles per hour out of our right front right now, being run off of this wonderful wheel over here, right? So now what I'm going to do is, can you bring that wheel up on the screen? Perfect. So I'm going to slow its speed down. I'll cut it roughly in half. And as you can see on the scan tool, we drop our speed, right? We'll slowly bring it up. And our speed is where it needs to be, right? So we'll let this flatline for a second. And then what I'm going to do now is I'm going to change our air gap. So I'm going to start to take this sensor and I'm going to start to pull it away from the wheel. So by spinning this, we're starting to change our air gap. And you'll notice that as I'm spinning this, nothing happens at first, right? Because we're at the point now where we're creating enough voltage, because we're spinning this wheel pretty fast, that we are able to overcome that trigger point. So it's going to take quite a bit to actually pull this thing away far enough to get it to not produce a high enough voltage level to give our signal or give our ABS module what it needs. There we go. Now we're running into some intermittent problems. So now we've increased our air gap enough at this speed to induce an intermittent failure out of our ABS sensor. If we back this away even further, we'll drop out eventually here. All right, so there we see it drop out. Now obviously this is an extreme case. If we can pull this thing up full screen, you'll see that we're not even close to 20,000th anymore, right? So you can see that's, let's go ahead and stop this. That's significantly larger than 20,000th now. We're at probably, I don't know, half an inch. But again, that's reading what, 11 to 14, whatever it was, miles per hour. let's go ahead and get this thing set back to where it was before at roughly 20,000. And let's bring our RPM really, really, really low as it'll read. Okay. So right there, we're spinning this thing super slowly. We're not reading at all. So let's bring our speed up really, really slowly until I can get it to react on the tool. All right. So that's 5 miles per hour. Okay. Now what I'm going to do is I'm going to start turning this real slow, and you'll see how much more sensitive it is, how little I have to actually increase our air gap to run into issues. Now it's going to make a liar out of me. Come on. So I'm actually having to increase it way more than I thought I would. But we're getting those intermittent issues. And then eventually we increase the air gap far enough and we have failure. So we're probably at about a 1/4 inch there at really low RPM. So that's what usually is going to cause our problem on these vehicles. Usually what we run into on these is rust builds up between the surface mounting of the sensor and the sensor itself. So where the sensor is mounted, rust builds up and it actually jacks that sensor away from the tone wheel, the part of the hub there that it's reading off of. And then we run into an air gap issue. That air gap is now changed and we have a lower output sensor. So I'm sure you guys have all run into this before and seen this. I wanted to share with you guys the actual scope data. And Keith has in here usually the hub wobbles. Okay, fair enough. It's possible that the wheel bearing itself could be failing, right? So if we have a wheel bearing that's failing, if it's not tight or it's wobbling or there's something going on with it, if that's failing, that'll cause our signal to, or our air gap to change. But we would see that probably at more RPM, right? We would see a signal wobble at higher speeds as well, because that bearing is moving. We would see that signal changing. We wouldn't see a consistent signal if we could maintain the exact speed that we're trying to. So on the scan tool, I would maybe expect to see some variation in that sensor instead of it holding dead steady. If we can hold a perfectly steady speed, that sensor should be flatlined, right? But if we're getting wobble in the bearing as it's going down the road, if we can maintain perfect speed but the bearing's wobbling, we're changing the air gap. If you're going slow enough and the voltage level is low enough, it might cause that sensor to go and have an intermittent issue. So wheel bearing wobble is an issue with these. It can cause this problem at very low speeds. So you always want to check your bearing and first of all make sure it's tight. This bearing is nice and tight. This is a hub style bearing, so it should be tight. Even on a 2-wheel drive vehicle, we don't have any slop or any play in this style bearing like a lot of 2-wheel drive trucks would, okay? This is a hub style and it's completely tight. So I think now we can actually go and get to the sensor itself. All right. And honestly, guys, if you were doing this in the shop, between driving this thing with the scan tool on it, throwing an ohm meter on it, making sure it's not shorted out, and watching the data, pulling codes, you're what, maybe 15 minutes into this job at this point. I just wanted to show you guys all of the data that's behind it with the lab scope and with this guy to show you why it happens, right? That's what we want to learn. That's what a lot of guys in the shop, a lot of you guys who do this for a living, don't have the time to understand or maybe look into the why or maybe do some of these experiments. That's why we went through with this thing and actually ran the vehicle off of that, is to be able to do that stuff that maybe you guys don't have the time to do. At this point, I mean, looking at the scan tool, running an ohm test, chances are I'd be pulling the wheel off, pulling the brakes apart, and looking at the sensor within 15 minutes of pulling the vehicle in. But, oh, Eric's out of here. See you later, Eric. Thanks for joining today. So I'm going to go ahead, we'll pull this wheel off, we'll pull the brakes off, and we'll see what we're looking at in here. So we had no wheel bearing play on here at all. It was nice and snug. So this thing probably doesn't even need a sensor. If, and that's a big if, this sensor can come out in one piece, I'd be willing to bet that we could clean off that surface that it mounts to, and we'll probably be able to get this thing to react the way it's supposed to. But let's get to that point first, and we'll see what happens. Generally speaking, these sensors don't like to come out in one piece. They have an O-ring on them, and rust builds up around that O-ring, and they like to get seized up in there. These do have the clips still on the rotor here, so this brake rotor's never been off, because chances are you can't get these clips back on once they come off. So it tells me our sensor has to be original, because you do have to pull the brake rotor to get this sensor out. So I'm going to just pull the caliper bracket. And never, ever, ever, first of all, safety first, right? Never let your caliper hang by the hose. You can definitely wreck the brake hose, so you can get some S-hooks or use some mechanics wire or whatever you want to use to hang that up. But again, never, ever let it hang by the hose. All right. These clips on here, if we can get the close-up shot on there, that'd be great. These clips are just installed at the factory to hold the rotor on when it's going down the assembly line. Usually a side cutters, you can get in there and kind of cut it. And safety glasses here, because these things can go flying. Otherwise, a hammer and a chisel works pretty good. Whatever you have handy, but they're not going back on. There's no reason to put them back on. All right, clips come off, and kind of rare, but the brake rotor comes right off. Didn't even need to be hit with a hammer or anything, or heated up. All right, I'm going to turn this back the other way so we can see the sensor. And hopefully not squish our caliper in the process. All right, so right there's our sensor. I'll zoom you guys in a little bit. Nice and rusty crusty in there, but it looks all original. And there, you can get this sensor out without having to pull the backing plate off. It's kind of a pain to do, but it is possible. Go ahead and just spray this down real quick with a little bit of penetrating oil in there, and if you can, leave it sit for a little bit and let it work its magic in there. But we're going to try to get this thing out right now, and we'll see if we fail, see if we break it off. Big nasty. It'll come right out. We'll see, Mike. I don't know. This has not been apart yet. I got all the tools ready for it, but I have not had it apart yet. So we'll hopefully not break the bolt off, and hopefully not break the sensor off. All right, that's a good sign. That came loose. All right, nice and rusty there, but that came out, so that's awesome. Grab a rag. Now comes the fun part. Now you want to be careful about twisting these sensors back and forth. In fact, there's even in the service procedure, it says don't twist, don't pry, don't do anything that's going to break the sensor. Well, it's kind of hard to get it out without doing those things. I usually try to get a screwdriver in here and just start wiggling. And, well, hope for the best. If we can go back to that shot there. But you can see how much rust is in there. But we just start wiggling it a little bit, up and down. Get a little bit more spray in there, try to get in there. And the problem is the O-ring. The O-ring is what gets hung up. So grab the new sensor here and I'll show you guys. Oh, by the way, this is part number AB 2017 is the part number for this vehicle. NTK sensors. Who else appreciates a sensor that comes in a sealed bag, right? I mean, just having a sealed bag for a sensor just tells me that it hasn't been installed or wrecked by anyone else. So that's kind of awesome. Also, comes with all the clips on it too. So, how many times do you guys break these? I mean, chances are I'll probably break them just taking this thing out. But what happens with these is this O-ring right here. That O-ring right there, we get rust build up on top of it. And because there's an O-ring in there, the plastic is thinner or thinnest at that point, and you usually break the sensor right at the O-ring. But we're going to try really, really hard to not break this sensor. So I'm just working it, wiggling it up and down, and something just cracked. I hope that wasn't my sensor. So it's loose, and the cup or the outer cap for the sensor is still down inside the hole. So we'll see if that is going to come out nice. Get this harness loosened up here. And so I think you guys can't see in there yet, but I can see the windings are exposed on this sensor, so it's not going back in the hole. So there's our broken sensor. You can see our winding of wires is exposed. We left the cap down in the hole. Now let's see if we can get this thing out, because, well, it's always a fun time trying to get this thing out. All right, we'll leave that off to the side for now. So be careful to try not to let any rust fall down in there if you can avoid it. You can see as I spin this thing, you can see the tone wheel actually moving inside of there. But we've left the side of this thing. Actually, we have the end of it on the sensor. The black plastic end is actually on the sensor. So all we've left in there is this portion right here. So maybe we can get in there with a pick and get that out. We'll see. I'm gonna get the sensor out of the way. So I'm just getting rid of, or taking out all the Christmas tree pins right now, and that one just broke off. That one came out nice. We'll get this guy out of the way here. You gotta kind of finagle it between this plate, and hopefully it'll come out. You might have to tweak the plate a little bit and remember to bend it back afterwards. There's a lot of rust sitting on this hub. And now I've already looked at the left front side, being the known good. I did pull the brakes off of that side, and that hub actually had been replaced. It has black lug studs on there, so that side had been replaced. And what I noticed with that sensor is that it had a spacer in between the sensor body. Oy. I don't remember this being this hard to get out. It had a spacer in between the body of the sensor and the hub itself. So if you pull your old sensor out, you pull that old sensor out and you have a spacer or a washer in between there, that is setting the air gap on that sensor. So what happens a lot of times when you put a new hub bearing in or hub assembly in that comes with a sensor, they may have, the manufacturer that may have bought that old assembly off of GM or whoever, and what they'll do is they'll shave down that surface, the mounting surface on the hub where the sensor goes in. They'll shave that down to get all that rust off of there. But then what happens is you've now decreased the overall air gap, right? You put the new sensor in, and it could potentially end up hitting the wheel because we've changed that mounting surface. So they put a washer in there to ensure that you don't, to ensure you have the proper air gap on there. But if you put a new sensor in and you forget to put that washer, that spacer in between there, you could end up ruining the new sensor because it could end up hitting the tone wheel inside of there. So keep that in mind, okay? If you ever pull the sensor out and you see a washer on it, make sure to replace that and put that onto the new sensor. Clean up the rust and everything on there and put it onto the new sensor. So I'm gonna go after this with a pick, and actually, if we can get might be able to get a really, really close-up shot here. I'll show you guys. That's not too bad, but I'll show you how this rust is flaking off in here. So take a look at this. See that? See that big chunk that I hopefully will keep from falling in? But look at how much rust is on there, guys. So we've definitely increased our overall air gap. And that's what's caused our issue. So we have a lot of rust buildup on the top of this O-ring here. So I'm trying to pick between the O-ring and the mounting surface, clean all that out, and then hopefully can pull this out. Sometimes you can use like, you could maybe thread a bolt into this plastic. You could try threading a screw into there and using like attaching it to your slide hammer maybe. That might pull it out. If I would have brought my slide hammer along, that would be nice. But we'll see if we can try to get this body of the sensor out without dropping it down into the bearing. I'm trying to keep my head out of the camera as well, so you guys can watch me struggle. All right, we should have some awesome background music, and if this was a recorded video, we could speed up the time. Grab a needle nose and maybe we can pull this thing out now. Back you guys up a little bit. And I may need to putz with this after we're done being live, because I don't really want any of this stuff to fall down into there, and I need to be very careful here. Unless you guys are enjoying watching the struggle. So here's that O-ring I was talking about. So how do you guys get these out? What do you got any tricks? What do you guys do? I really don't want to give up. So right now I've just pushed it down into the tone wheel itself, so that way I can try to get it split in half, and hopefully it'll slide right out. Hey, there we go. So split it in half, and out it comes. A little bit of struggle, but I think overall we're making time on this one. I think it's quoted at over an hour. So extractor. Hey, there's a J tool for it apparently. If the hub is already 5+ years old, replace the hub makes sense. Yeah, I could agree with that. If the hub bearing itself is older, sure, you could just replace the hub itself. But this customer is cost conscious and wants to fix this thing the right way with quality parts without having to put in let's call it an unnecessary wheel bearing, because this thing is not noisy and it's not loose. So I would say on this one we will be just fine putting a new sensor in. So that's what we're doing. So I'm going to clear away some more of this rust on here, and you can see there's even some rust down in the hole. And then we'll take, and you could use I'm just using some emery cloth here, and we'll try to get this thing all cleaned up. Maybe. It's a lot harder on these because you have to get in between the hub assembly and the backing plate there. But again, we're just trying to get a smooth, rust-free surface and try to get all that stuff that's potentially falling in the hole out of there. And if you look down in this hole in here and you see a bunch of metal shavings in there, chances are your hub bearing is failing and you'll want to replace it. This one looks good. There's no shavings or anything down inside of there, so we're not going to be, again, just another reason to not have to replace this one. So we got our surface down. If I had some anti-seize sitting around, I would throw it on this surface, but we'll just use some of the grease that this thing came with. So it came with a little bit of grease here, and it also came with a new bolt with a little bit of Loctite applied on that. So that's nice. Don't have to reuse the old rusty bolt. So I'm going to take just a little bit of this on my finger and just kind of go over all the mounting surface here. Again, if you have some anti-seize sitting around, that would probably be good for this. Fortunately, I don't have any here. And then always, anytime you're installing something that has an O-ring on it, make sure you lube up that O-ring first. Where did I put my new sensor? Here it is. So again, a little bit on my finger and then just around our O-ring on here. And back through the wonderful, now bent out of shape backing plate that I need to remember to bend back. Otherwise we'll have a nasty brake noise. And it slides right in. Click, click, torque to spec. And we're good to go. All right, so our sensor is installed there. We put it back. Always put your sensors back in their homes. Otherwise, you can run into this thing getting stuck, hung up on something, you can have a lot of issues. So always put the sensor back. Try and pound this Christmas tree pin through, or out if this is even a through hole. Well, I'll mess with that later. That's not going to affect our signal. So we can retest this guy. Plug it in. There we go. So after I fix this one Christmas tree pin here, I'll just have to pound it down through the hole. But once that's fixed, this job is done. Put the brakes back together, and we're all done. Now we'll do a little bit of follow-up testing here. I just want to see if you guys have any questions before I put everything back together. Torque to spec, exactly. All right, throw the brake rotor back on here. Actually, we'll turn the wheel back the other direction first. And again, if you had NACs around the brake hub would be a good idea. I'm going to have to pull this back off, and I'll clean all this back up afterwards. But don't want to waste any more of your time. We've already been here for an hour. So we'll just slap this back together really, really quick to retest this thing with the wheel back on it. Because I could spin this by hand at the hub, but that's not the way the other side is apart right now, and I want to be able to get roughly the same speed on both wheels so we can show that. But if you're just looking for verification on it, you could just spin it right at the with just the hub. Like I said, this is all coming back apart again, so you'd want to obviously torque these bolts. A lot of them have Loctite on them, so if it came out with Loctite, clean them off, put some new Loctite on them when you reinstall them, torque them down, clean up your hub surface so you don't have excessive rotor run out, and then when you torque your wheel, when you put your wheel on, make sure you torque that as well. And then we have to move our brake shield, because I think right now, obviously it's hitting, so instead of figuring that out on the test drive, it's a good idea to do that beforehand. All right, everything's plugged in. All right, so that's all there. Uh-oh. We'll fix that up later. I'm gonna go ahead and back probe at this sensor now. I don't want to pierce it at this point because well, it's a brand new sensor, it's a brand new harness, it's a shielded harness. I'd rather not pierce if I can avoid it. So I'm gonna back probe into it, and we'll do a little bit comparative testing. Scan tool and lab scope. All right, we'll see if that's reading. The only downside again with back probing over piercing is it's a little less accurate. I usually have to fumble with it a little bit to get it to read. We'll see how we do here. Yeah, that wasn't so bad. So aside from the horrible noise of the rotor hitting the brake shield, let's actually we can you can see that we're already starting to create so again, it's spinning that slow speed. We're able to get this thing to work. And again, roughly the same speed on the other side. And wasn't fast enough, or I don't have the sensor plugged in, one of the two. All right, so well, that was a little bit faster. But actually, take a look at that, guys. Our new sensor is creating more voltage than our other one. So that's nice. It's good to see. So now we're peaking. So even at that low speed, we're half a volt at least. Where the left front, the known good side, is 230. So our new sensor looks to be more efficient than our old sensor. It's creating a better magnetic field, which is in turn creating a higher voltage output. So overall, our new sensor is more efficient. Now, it's hard to say if that left front, which we're calling a known good, you want to switch back to the main camera? It's hard to say if that left front, being a known good, is as efficient as it could be. Because this is actually owned by us, this is actually owned by the company. I have another sensor for it that's going to go in on the right side. Excuse me, the left side. Both sides are going to get new sensors just because it's already in here, it's already a part. Might as well throw them in. But it does look to be that the new sensor is putting on more voltage than the old one. So it should in turn be more accurate, more sensitive to those low speeds. But again, after we've crossed, the biggest takeaway here, guys, is after we cross that voltage threshold, after we cross whatever number it is that the ABS module is really looking for, then we're really looking at frequency. We're looking to see at whatever it is, trailing edge or leading edge, whatever it might be. If you want to bring up the scope here, all we're looking at is we're looking to, let's take this dotted line right here, for example. Let's say this dotted line is what's required by the ABS module to say the wheel is spinning, to start to read our peaks. So let's say that that's at 227 millivolts, okay? So about a quarter volt, maybe, we'll say that this vehicle requires to start to pick up. Then we start measuring the frequency, or the time between either leading edge or trailing edge at a certain voltage level. And again, that's going to be proprietary to the ABS module, to GM in this case, or whoever made the module for them. But it's going to be looking at a certain voltage value at a certain leading or trailing edge. So maybe it looks at the leading edge on every peak at 2.5 volts. Okay, maybe that's what its measuring spot is. 0.25 volts, or a quarter of a volt. So a quarter of a volt, maybe it's looking at the leading edge, or maybe it's looking at the trailing edge, or maybe it's looking for, well, it's not really going to look for the peak. It's not going to be able to notice the peak. It's looking for either a leading edge or a trailing edge, and then it'll compare it to the next trailing edge, and the next trailing edge, or the next leading edge, whatever it might be. And that's how it's able to determine the wheel speed on that specific wheel. So again, changing air gap, taking that sensor, putting rust between its surface of the sensor and the hub. When we change that air gap in between there, we're making that sensor essentially less sensitive at very low speeds, very low voltage output levels, okay? Once the speed is fast enough, we see that sensor start to respond, right? We see it cross the trigger point. We see that very sharp line on the scan tool, okay? Any questions? Whole bunch of comments. Unfortunately, I haven't been able to really monitor them too well because the laptop doesn't seem to be letting me onto YouTube right now. But do you guys have any comments? More sensitive is a new word for out of spec. Sure, sure. All right, I don't see any questions. Anybody got any questions? Yes, I'll be at Vision this year. If you guys haven't signed up for Vision yet, make sure to sign up for that at the end of, end of February, beginning of March, right? Last weekend of February in Kansas City. Sign up for that. But I will not be going to TST this year. Too much going on at the beginning of the year. Oh, the shirts. I forgot to mention that in the beginning. Guys, we're working on getting new t-shirts, okay? That's why there's no trivia question this time. Normally we would have the trivia question, have you guys email in your answer, you would win a shirt. We're going to be doing that again. It just is going to take us, hopefully, fingers crossed, February 7th class, next month's class will have new t-shirts, okay? Hopefully, that's the hope, that we'll have new t-shirts for you guys to win. Okay. Where's Glenn? You mean Ozstar Glenn? He had a meeting today, I believe, some sort of meeting. Yes, we'll send to Canada, but you guys who are out of the country here, out of the USA, only have the opportunity to win one shirt due to shipping costs and everything across the border. Chuck asking how you sign up. Chuck, when we do the class that has the t-shirt in it, my email address will come up on the screen, and then you'll have your trivia question with the answers up there, and you'll just send me out an email with your answer. If you get it right, you'll get a shirt. Any other questions about this? I guess that's kind of ABS in a nutshell. Oh, I guess to throw one more thing into this. Now we're seeing different style ABS sensors, right? They're not all two-wire variable reluctance voltage creating sensors, right? A lot of newer cars are running Hall effect or magneto-resistive sensors. Be very, very careful when you're diagnosing that type of sensor that you're going after it in the right manner. Changing air gap on something like that can completely change its output, okay? So if we take a Hall effect sensor and we were to put it in here like this, we would read that, so on a Hall effect sensor, it's powered up, it's grounded, and we have a signal, right? And it's going to read a square wave. So every time it passes the leading edge and trailing edge on our wheel here, if we can bring that up on the screen, every time a Hall effect sensor passes this side and this side, we're going to see either it go high or low, okay? But what happens when you change the air gap on that style sensor, if we take this thing and we back it way up here and we create a large air gap, we're going to go from reading that perfect 0 to 5 square wave or 0 to 7 or 0 to 12 square wave like what we're looking for. It'll be perfect and then it'll be gone. It'll drop out. Or it'll be an intermittent problem, okay? We're not changing the amplitude or the voltage level on that style sensor, okay? It's only going to be on a variable reluctance style sensor, okay? So keep that in mind with air gap on Hall effects and magneto-resistive style. And we'll probably do a class on that in the future as well. Did I check for TSBs? Unfortunately, I did not on this one, but it would be a good idea to check out a TSB. Mike from Robinson's Auto Diag is saying he believes in 07 the trucks had both options. So again, you'd want to check the wiring diagram, probably compare it against the build date or the VIN to verify what style sensor it is that you're diagnosing. Because you want to know what you're looking at before you go in with an ohm meter or a, scan tool can probably interpret whichever, but with an ohm meter or a lab scope, you want to know what you're looking for. After repair voltage, you want to see that with a meter? We can do that real quick. Let's find my leads. And we'll spin this guy around and see what our low speed voltage is on the meter, because I have a feeling that's probably what a lot of people are going to be using. Again, we're on AC volts on the meter, okay? Don't do DC. And we're back probed into the sensor. All right, can we go with the close-up camera here? I think we'll be able to grab the, maybe. So, I don't even think we crossed 100 millivolts before, or 0.1 volts before. We're seeing a significant difference. And actually, if we bring up the lab scope down in the corner, I'll just show you guys the difference here. Okay, so again, we're spinning 200, 300-ish millivolts is being created by the sensor right now. But if we look at the scope, we were peaking here at almost half a volt. So just remember, with the meter, you'll always read a lower overall AC voltage level. But at this point, we're just looking for that proper level to bring that sensor online. So actually, I think we're plugged in, and that's about how fast it takes to get the scan tool to react to 4 miles per hour. So that's about how fast you want to spin it. Again, it's way easier on a 4-wheel drive vehicle or diagnosing a rear ABS issue, because then you can use the vehicle to power it and monitor side to side. But overall, you're just looking for over 150 millivolts probably when you're spinning it by hand at a slow speed. You should be able to overcome that and see the scan tool react. Now, if we had an open sensor, we wouldn't have any reaction out of the scan tool, so that wasn't our problem. Couldn't have been our problem. We were able to prove that out right away. May want to check the torque on those 2 lug nuts. Disclaimer, these lug nuts are coming back off. I'm pulling this wheel back off to torque down the brakes, to fix one of the Christmas tree pins in there. So this wheel is coming back off. This vehicle will not leave without all of the lug nuts torqued in place. All right, I think that's about it unless anybody had any other questions. Cable TV is a waste of money. All right. Oz, I'm not sure what we're going to be teaching next month. That's kind of the fun of doing this live is, well, I have 30 days to figure out what we're doing in February. So I'm not sure what's going on yet, but fingers crossed I'm going to be able to get you guys out another video this month on a vehicle that I worked on that I recorded, what was it, maybe a month or 2 ago on a window circuit issue on a mid-2000s Infiniti G35. So I got that one recorded, got to work on the editing for that, get that one out. But look for that one later this month. Yes, Chuck, the voltmeter is too slow. That's exactly what the problem is. The voltmeter is only reading a certain amount of times per second, where the scope is reading millions of times per second, okay? So we're looking at that signal less often, giving us a lower overall voltage. All right, guys, I think that is it. So I really appreciate you all being here, sticking with it for an hour and 20-minute ABS repair that a lot of you guys would have thrown a sensor or bearing in after 10 minutes of checking it out. But it's good to be able to know the why and see how we can change things and manipulate things to show what actually is happening on the vehicle, because not every single one is going to be as simple as seeing it on a scan tool and saying, yep, it's the right front. What happens when this is an intermittent issue that happens every other week on a rainy day? You get it into the shop. You can't just say it's not acting up, send it on its way, right? I mean, you're putting business out the door that way. It's a good idea. Get out the voltmeter, get out the lab scope, check your voltage levels side to side. You know, see if there's something that's sticking out. See if you have a varying voltage level, right? If this one is half of the other side, there's a good chance that the voltage level on this side being half is the problem. And even though it's not acting up consistently and you can't see it on the scan tool maybe, it's a pretty obvious inclination or a pretty obvious thing to see that we have an issue with this side. So you're not going to see them all on the scan tool. I drove with one of the guys that works here, Paul, drove with him, maybe it was 3 months ago or so now, and he had a false activation on his Silverado. We drove, we used the scan tool, tried to look at it with that, but it was reading exactly the same for every single wheel. There was no discrepancies in that one at all. So we couldn't look at it with a scan tool. We did have to get the lab scope out to be able to look at that one and be able to figure out which wheel that it was. So just keep that in mind. Voltmeter, lab scope, whichever tool you have, they're both going to give you an idea of what you're looking for. All righty. It took way too long, yeah, for sure. So that thumbs down is gone now? That's awesome to hear. All right, guys, if you liked what you saw, please do the thumbs up, hit the subscribe button, hit that little bell icon or whatever so you get notified when we go live. And we're going to be live again on February 7th at 11 a.m. for the next one. And like I said before, I don't know what we're doing yet, but I'm sure it'll be something fun, something interesting. I have that, you guys remember those wires that I spliced together with like twisting them together? One had a wire nut, one had like a solder connection, all those, and I put them on my truck to let them kind of get corroded. Well, they're still on there today, so that one's kind of in my back pocket. We'll see if we get something interesting for February. Otherwise, we're going to do that. We're going to see what those connections look like over time. All right. Well, thank you guys for watching. I really appreciate everybody being here and sticking with it for now an hour and 25 minutes. So until next time, we'll see you guys then, and happy wrenching, everyone. Thank you.